Hey everyone, and welcome. Today, we are jumping into what is, no exaggeration, the absolute bedrock of all calculus, the idea of limits. It's actually a pretty simple concept, but it's the key that unlocks some of the most powerful and fascinating problems in math. So, let's get right into it.
So, we've all had it drilled into our heads, right? You just can't divide by zero. It's the one unbreakable rule. It's undefined, a total dead end. But what if we could get infinitely close to zero without ever actually getting there? What would that look like? Well, that's the exact kind of puzzle that calculus, using limits, was built to solve.
And that question leads us right to the heart of it all. See, a limit isn't about what a function is at a specific point. Nope. It's all about the value that function is heading towards, the destination it's approaching as you sneak up on that point from both sides. It's kind of like the old saying, it's about the journey, not the arrival. So let's really unpack this. And the best way to start is the most intuitive way, by just looking at a picture. How can we actually see a limit on a graph? Now, for a whole bunch of functions, the ones we call continuous, this whole thing is honestly super straightforward. The value the function is approaching is just, well, it's the value of the function right at that spot. The path leads exactly where you'd think it would. It's the happy path, no surprises. And what do we even mean by continuous? Well, there's a fantastic, really simple way to think about it. A function is continuous if you can draw its entire graph without ever lifting your pencil off the paper. If it's just one smooth, unbroken line with no breaks, no gaps, no sudden jumps, you've got a continuous function. Okay, but what happens when you do have to lift your pencil? This is where functions start to misbehave. And honestly, this is exactly why limits are so incredibly powerful. They give us a language to talk about what's happening at all those messy, broken little points on a graph. So here we're breaking down the two main ways a function can act up. On one side, you've got a hole, or what's technically called a removable discontinuity. Think of it like a single paving stone that's missing from a path. The path is clear, you know where it's going, but that one specific spot is just gone. On the other side, you have a jump. This is way more dramatic. It's like the whole path breaks and suddenly continues on a totally different level. In both cases, you gotta lift that pencil.
And this brings us to a super crucial point. A limit doesn't always exist. Sometimes you'll see it written as DNE, which just stands for does not exist. This happens if the function is heading to two different places from the left and the right, like in that jump we just saw. It also DNEs if the function just shoots off to infinity, or if it just wiggles back and forth like crazy forever without settling down. In those cases, there's no single destination it's approaching.
Okay, looking at graphs is great for building intuition, for sure. But most of the time, in a class or on an exam, you're just given an equation. So how do we find the limit when we can't actually see the picture? Well, for that, we're going to need our algebraic toolkit. This right here is your game plan. It's a simple three-step process you should follow every time. Step 1. Always, and I mean always, try just plugging the number straight into the function. If you get a real number as an answer, that's it. You're done. But if you get that dreaded 0 over 0, that's your signal to move on to step 2 or 3. I absolutely love this quote from our source material. Getting 0 divided by 0 isn't actually a world-ending paradox, but it sure feels like one sometimes, right? But really, all it is a signal. It's the function's way of telling you, hey, there's a hole here. You can't just plug in the number directly. You got to be a little more clever about it. And that is where factoring comes to the rescue. When you factor the numerator and denominator of a fraction and you cancel out a common term, what you're doing, algebraically, is patching that little hole in the graph. You're finding a new function that is identical in every single way, except at that one missing point. And once the hole is patched, you can finally just plug in the value and see where the function was heading all along. But what if you run into a function that's just too complicated or messy to factor? For those really tough cases, we need a sort of power-up. It's like a secret weapon for limits, and it's called L'Hopital's rule. So how does this magic rule work? It's actually shockingly simple to use. If you try to plug in your number and you get 0 over 0 or infinity over infinity, L'Hopital's rule says you can just take the derivative of the top part and the derivative of the bottom part separately and then try to take the limit again. It is an unbelievably slick trick for solving problems that look completely impossible at first glance. And the real power here is that this rule cracks open a whole family of these tricky situations, which are called indeterminate forms. An indeterminate form is basically math's way of shrugging its shoulders. It's a result like 0 over 0 that just doesn't give you enough information to figure out the limit. L'Hopital's rule is the systematic way to get that information and find the answer.
All right, so far we've been zooming in asking what happens as we get closer and closer to one specific number. But what if we asked a totally different kind of question? What happens to a function if we just let our input x get bigger and bigger and bigger and just let it run out towards infinity? This table lays out the rules of the road for rational functions, and it's really all about a race to infinity. Just think of the degree, that's the highest power of x, as the speed of a runner. If the denominator's runner is faster, the whole fraction gets pulled down to 0. If the numerator's runner is faster, the fraction blows up and shoots off to infinity. And what if they're tied? Well, then it's a photo finish, and the limit is just the ratio of their leading coefficients.
And what does the answer to that limit problem actually tell us about the graph? It gives us another key feature, the horizontal asymptote. A limit at infinity tells you the y value that the function's graph levels out at as it stretches forever to the left and to the right. It's the ultimate long-term behavior of the function.
So let's wrap this all up. When you boil it down, from dealing with division by 0 to figuring out what happens at infinity, limits are the fundamental tool. They are the language that calculus is built on. It's what allows us to talk with precision about the infinitely small and the infinitely large.
And that leaves us with one final and I think really exciting thought. We have now mastered this art of getting infinitely close to a point without ever actually touching it. So what does that let us do? What kind of amazing new things can we build on top of this foundation? Well, that's where things like derivatives and integrals come into the picture. And that's a story for another day.